In this video we're going to be looking at how to conduct a hypothesis test on the sample mean for the normal distribution. Quite a common hypothesis test. Basically what we've got here, imagine you're taking a sample, imagine we have a distribution with an assumed, which we know is normally distributed, with assumed mean and unknown standard deviation. Imagine we take a sample of size n and suppose a sample of size n is taken. Then what we get, and we've actually looked at this in more detail in the previous video, something called the sampling distribution, which has got basically a same mean but a tighter standard deviation, what's called the standard error of the distribution. So the distributions will be, if this is our original normal distribution, then our sampling distribution should have the same mean but a tighter standard deviation. So that would be our distribution of sample means. So suppose we have we take a sample of a particular size and we get the value of a mean of a particular value. That doesn't mean that we know that what the actual mean of the original distribution is, because we don't know that. But we can kind of make a hypothesis about it based on perhaps previous information, what we think it was previously or whatever. And we can make a hypothesis based on our sample on what we think the actual mean is, but we don't know what it is. That's quite important. That's basically the whole point of the hypothesis. An important caveat here in this whole test here is that we assume standard deviation is known. For some reason, it might be because of previous experience that we know the standard deviation is known from for some reason we know what the standard deviation is for this test. So we're not testing on the standard deviation, we're testing on the mean. Mean is not known because we've taken a sample. And I say this whole idea of a sampling distribution is that, yes, we don't, for one particular sample, we don't know the mean, but the distribution of all possible samples of size n will be normally distributed with same mean, mu, of the actual parent distribution, but with a standard deviation called standard error, which is reduced by a factor of square root of n. Okay, so that's how that's the distribution we're going to work with when we're doing our hypothesis tests. I'm going to run through this with an example. I'm actually going to use might seem a bit like overkill, but I'm going to go through 3 different methods for doing this question that we come up. One is just testing probabilities. That's a bit like, I probably should have said at the start, this is really aimed at A-level students in England, Wales and Northern Ireland. Any of the boards really, because on all of them. This is really a very basic but kind of approach, but I'm including it here and it's perfectly acceptable because it's more similar to the approach that you should already know on hypothesis test with a proportion on a normal distribution. So it's a normal distribution on a binomial distribution. So it's more similar to that. The second one is using z equals to x bar minus mu over the standard error as test statistic. And I must admit, this is the one I tend to use, but that's out of habit. If you actually look at previous videos on this, this is the one you'll probably see more. It's perhaps more common. but really there's no, either of these two is acceptable, but it's a little bit more involved as method 2, but you're going to see it a lot more. And of course it depends on, thinking in terms of the examination, you probably ought to know all of these, because they might word the question in such a way as to kind of force you or really make it difficult to actually go, to actually go with your preferred method. So you really ought to know these all approaches. Really, I would if I was doing it. The third method is more involved, but it involves the critical region. Find critical region. And that's actually quite a key idea in stats in general. Critical region, I spelled it wrong, haven't I? A critical region is something you've sort of already seen when it comes to binomial, is the set of values for which H0 is rejected. So what you do is test whether it's in or out of the critical region. So there's some key things I'm going to cover. There's some key ideas here. The idea of test statistic and the idea of critical region, a kind of vocabulary that they will expect you potentially to know. Okay, so let's do a question. I'm going to go through all three of these approaches. And I say, I don't think it's a case of choose your favourite. Method 3 in particular is something that you are expected to know what critical region is, and you shouldn't be put off by kind of technical vocabulary like test statistic either. So here we go. Here's a problem. Here's a question. Right, okay, so this is an old AQA A-level maths question, and it's about in previous years, the marks obtained in a French test by students attending top-notch college have been modelled satisfactorily by a normal distribution with mean 65 and standard deviation 9. Teachers in French department at top-notch college, you like the way that examiners kind of have a sense of humour here, suspect that this year their students are on average underachieving. That's quite a key word, because that suggests it's going to be a one-tailed test with the inequality in that direction, that the actual students of this particular college are not doing as well as they are as the general population. In order to investigate this suspicion, the teacher selects a random sample of 35 students to take the French test and found that their mean was 61.5. Investigate the 50% of level of significance the teacher's suspicions. Okay, so right, I'm going to start just defining a few things. So let mu be mean score. The mean score of students, or let's just say expected mean of students of top-notch college French scores of students at top-notch college in this particular year. It's difficult to get the wording right there because of the unusual kind of circumstances of this test, but it's best to try and, because it was about, whether this year's French marks are actually lower just by random kind of chance, or whether they're actually worse than normal. So that's the way why I've been a bit careful with how I've defined it. So we actually think that mu is what we would expect their mean to be in a top-notch college. So that's what we defined it. That's what we defined in this particular year, and we would expect it to be the same as I suppose we don't really need the particular year bit. Is the expected mean that mu be? No, it isn't, because that's what we're testing in this particular year. Because we want to know whether the mean in this particular year, the expected mean, is actually worse or better than the it's not better, but whether they're actually worse than what the long run mean we know to be is. So that's, and we don't know, that's the point. We don't know. What we want to know, whether 61.5 is significant or not. Okay, now you probably wouldn't lose any marks for this, but I think it's important just as a learning point, just to say we are assuming standard deviation sigma equals to 9, you say unchanged. So this test relies on, theoretically at least, that we know what the standard deviation is. So our null hypothesis is that mu equals to the same as it always was, 65, and our alternative hypothesis is that it's actually less. These students just aren't as good. Okay, that's the alternative hypothesis, because it's and what we do, and the basic philosophy is this: we do all our calculations based on the assumption that mu is 65, and then if it just so transpires that that's unlikely, that's sufficiently unlikely within the kind of tolerance we're given, within the significance level we're given, we kind of reflect back and then conclude that it's actually, that this H0 or may or may not be need to be rejected under a certain kind of level of under a certain significance level of uncertainty. Okay. Right, so let's just do method 1 now. So this would be the same. Obviously, this bit would be the same for this bit would be the same for all 3 methods. So method 1 is the most basic one, but all of them. In fact, I might just slip this in before the let's say method 1. All of them, the sampling distribution, assuming the mean is the same as it was ever before, is going to be normally distributed with mean 65, and standard deviation or standard error, or let's write the variance down here. The variance is equal to and I say this is assuming this is unchanged, is equal to 9 squared over 35. A standard error is 9 over the square root of 35. So let's write that down. So that's the same for all of these tests. We're going to be working with that distribution because we've taken a sample of size 35. So that's going to have a tighter standard deviation than the original distribution. Right, okay, so let's just do method 1. That's just find induct probabilities. And what we do here is just find a probability that the sampling distribution would be 61.5 or something even less likely than 61.5. So basically what we're doing is we're finding what the probability of 61.5 is and what this value is along the tail here. And if that is less than 5%, then we're going to be rejecting H0. If we're working that out and assuming that this is 65, work out what that is, and if it's less than the 5% significance level, we then actually conclude it's not actually, perhaps not actually, the mean is 65 and it is less than that. Okay, so we're going to use a calculator for this. So let's just go for menu 7, PD. Right, now we need to kind of give a lower value because we're on the lower end of the tail. 0 is going to be plenty small enough because the standard deviation is quite small and it's 65. 0 is way off, very, very small for this distribution. So that's good enough. Upper 61.5. The standard error or standard deviation of the sampling distribution, make sure you put the standard error in, not the variance. So it's 9 divided by the square root of 35. And the mean, the assumed mean of this distribution is 65. So we've got 0.01070. Now that is less than 5%. So we're actually, so it's kind of 1.07% basically. So we actually conclude we reject H0. There is sufficient evidence at 5% level, but you don't have to write that, but some people do, but you don't have to as far as the examiners are concerned. There is sufficient evidence to suggest, and we need context as well, this year's students at top-notch college are underachieving in French. Underachieving in French. Okay, so method 2 is slightly more involved, but you're going to see this more often, so I feel that I ought to include it, because this, and it's also quite a nice way of kind of talking about what we often do, the kind of technical statistical language we use. And one of them is test statistic. And it kind of is more intuitive statistic. Can't spell statistic. Okay. It's more intuitive in this case because basically what we do is with the idea of test statistic, we work something out and then we test it against what we would expect it to be if H0 was what we've made in our null, if the value of mu was what we made in our null hypothesis. So we use this and we test it with what we expect it to be. So what we need to do is find critical values of Z. So now to do this, you can you can go to the tables that you get in the exam in all of the A-level boards. I think we'll have tables that give you this, but to be honest, I think it's just as well to use the calculator for this. We're working with the standard normal distribution because that's what all this is about. We're transforming it to the sampling distribution to the standard normal distribution, which has got mean 0 and standard deviation 1, and we're looking at what these values would be either end here, where there's, because it's one-tailed, where it's 5% this side or 5% the other side. Okay, so let's bring up the calculator. Okay, so let's bring up the calculator. Okay, so we can use it to either find the lower value or the upper value, or both. To be honest, we're wasting our time doing both because they're going to be symmetrical. We're going to have a negative value for Z here because the mean is 0 and a positive here. So we can either put, to work this one out, we can put 0.005 for our area. 0.05 for our area. Mean standard deviation 1, mean 0. That gives us the value minus 1.645. Or if you prefer, or you could use it as a check, if you put 0.95 in that area, in that one, you're going to get, and we shouldn't expect that by symmetry anyway, positive 1.6445. So what we do is we test what the value of Z actually is for our particular outcome here. So we test that. Let's change your pen again. So Z equals So the value of our test statistic Z is x bar, which is 61.5, minus mu, which is 65, all over sigma squared over the square root of n. And that comes to no, we need to put the actual values in. We're assuming the standard deviation is equal to 9, and so therefore the standard error is 9 over the square root of 35. So that comes to minus 2.30. Okay, and minus 2.30, and we're obviously in here in this part here, so we're down here. 3 minus 2.30, so that's basically less. That number there is less than our critical value, so therefore we reject H naught. It just occurred to me whilst I talk about this, this is one tail, so we really wouldn't be wanted to see anything. We weren't, because we were asking whether they were underachieving, so we really didn't need to look at the top and tail, but the test still stands, so that's fine. It's less than the 5% level that it would need to be, and yeah, that's it. If it were two-tailed test, then we would be splitting it both ways with 2.5% each side. Okay, but it's one-tailed, so it's 5% just on the left-hand side. So I was wasting my time looking at the right-hand side because we knew it was going to end up there. But it doesn't make it wrong; it's just unnecessary. Okay, so we're looking at the left-hand tail. That number there, changing the colour back to blue. So that number there is less than our kind of critical value, minus 1.6445, or if you prefer to think in moduli form, you can say it's more than you could say like the modulus of it is actually more than the modulus of minus 1.6445. Either case, we're kind of in our critical region for Z, if you like. We're beyond our critical value, so we reject H naught and all the rest of it. So method 3 talks about finding the critical region. You do need to understand what we mean by critical region. In this context, it's the set of values of possible values values of the mean that you've actually found, of the mean of your sample, for which we reject H naught. Okay, so I did say early on that this is most involved, but actually thinking about it, with the calculator we're allowed to use now, it probably isn't, because we can use the inverse normal with our, remember, just going back to our sampling distribution is normally distributed with mean 65, assumed mean 65, and under the null hypothesis, and an actual assumed mean variance of square of 9 over 35, or standard error of 9 over the square root of 35. And what we can do is we can actually look at the values of our, if this is our distribution for x bar, we can relatively easily, using our calculator, find the values here for which we would reject. This needs to be 5%, and we can find the values of x bar for which we would reject it using the inverse normal. So let's do that now. So we have menu 7. And we want inverse normal now. It's I have this from the previous time I used it, so it's 0.005, that's fine. But we're actually working with our actual standard error here, which is 9 over the square root of 5. and our mean is equal to, or I presume mean under the null hypothesis is 65. So that's 62.5 to 3 significant figures. So any numbers below 62.5 we're going to reject. So basically the critical region is approximately X bar is less than 62.5. Don't need to worry too much about being accurate with the boundary here, because we've got 61.5. So we can therefore conclude that 61.5 is in critical region. Okay, it's in critical region, and therefore we can reject H0, and we can come to the same conclusion as we did before. Okay, reject naught. There is insufficient evidence. There is sufficient evidence to suggest this year's students at Top North College are underachieving in French. So there you go, 3 possible approaches. I think you need to kind of get your grips with all of them, particularly method 3 and maybe 1 or 2. You could, I suppose, forget about method 2 or 1 if you wanted to. But I think it's good to see all of them, because the more confident you are with the different kind of ways of approaching it, the less you're going to be put off by the particular way an exam question is phrased. Okay, the only thing I'd say is that this was a one-tailed test. I have mentioned it during the video. If it were two-tailed, obviously you need to be sharing the that hypothesis level, that hypothesis at significance level on both sides, but that didn't happen in this particular example. Okay, I think that's a good point to stop. Bye.